Hello everyone. In this video we are going to talk about vector space isomorphisms. So I'm sure you're wondering what this big word isomorphism means, but first we need to recall a fact from before. So let's recall that a bijection is a function that is both one-to-one and onto. So in this video, we're only going to consider functions between vector spaces. So let's say we have a function f from v to w, where these are both vector spaces, potentially the same. Then recall that f is one-to-one if whenever you have two inputs with the same output. So whenever you have, say, f of v1 equals f of v2, these are both in v, then v1 is equal to v2. Right, and f is onto if everything in your target space, so w here, has something going to it. So if for any w in w, there exists a vector v in v such that f of v is w. Okay, and so why is this important, or what does this really mean? It basically gives us a matching between our two spaces, right? So if you have v over here and w over here, the idea is one-to-one means that you're not going to have two guys going to the same one on the right, and so, these all have to go to different things. And the fact that it's onto means that everything over here has an arrow going to it. Right, and so basically this means that you're going to be able to do a nice matching between elements of v and w. And this is going to be part of what is required to be isomorphic. So what does it mean for two vector spaces to be isomorphic? So basically it is a notion for us of sameness. So I think it's best expressed through some examples. So for instance, if you see vectors, column vectors in R3, right? They look like ABC. So this is stuff in R3. Now, what if I consider matrices in M1 by 3? Those are rows, right? And so they look like some ABC, except I wrote it in a row instead of a column, right? It seems like these things should behave pretty similarly, right? Because it's just the difference between writing a row and a column, but both of them have three entries. When I add things or scale things, they kind of behave in the same manner, right? It kind of works coordinate by coordinate. So it seems like these behave the same. Now you've seen something else that behaves the same as R3 as well. What about P2? What does a general thing in P2 look like? Well, it looks like maybe an ax squared plus bx plus c. And of course, we note that what really matters here when you start adding these or scaling these polynomials, is the coefficients change. And you have already been using coordinate vectors a lot, right? Going through polynomials and then turning it into column vector form so that you can use matrix computations to do things. So basically, we've already said that these things basically seem like they're the same. They're written differently, but they should behave similarly. So an isomorphism is a way to make this precise. So officially, a function, so it must be a function, f from v to w to vector spaces is an isomorphism if two things hold. So first, if f is a bijection. So if it's one-to-one and onto. So this basically gives us like a matching between the two. But just a matching is not enough, because it's important that these are vector spaces. And so we also want this function to, quote unquote, play nicely with the structure of being a vector space. And so we're going to say that it preserves structure. So what do I mean by this? To be more precise, it's if two things hold. So it's under addition. So basically f of v1 plus v2, basically if I add in v, this should be the same thing as if I took it over to w and took the two things matching and added them up after applying the function. And same thing with scalar multiplication. So f of some r times a vector v is equal to r times f of that vector. So just a bit of vocabulary and notation. So if this F is an isomorphism, then we say V is isomorphic to W, and you write it using this equal sign with a tilde on top. Okay. So let's take a second to examine what this preservation of structure means. So the idea here is, like we said, that R3 and P2 should be the same, right? So if I have like 1, 2, -1, and 0, 1, 3, right? Then basically what this is saying is it shouldn't matter if I first correlate these to x squared plus 2x minus 1 and x plus 3 and then add them, right? Because this is going to be x squared plus 3x plus 2. Or to first add them, in which case you get 1, 3, 2, and then correlate, right? That it doesn't matter which way you do things, in what order, you should get the same thing either way. And that's true. So this would be like property A, and you do the same thing with scalar multiplication. So let's now show like what it looks like to prove something is an isomorphism rigorously. So we claim that R3 and P2 are isomorphic. And what is the isomorphism? So you can do it really either way. We'll start in R3. So we'll do it so that f of ABC is ax squared plus bx plus c. So first, right, we have to show this is a bijection. So is it 1 to 1? It's the first question. So suppose f of a1, b1, c1 equals f of a2, b2, c2. Then what must be true? Well, this is just saying a1x squared plus b1x plus c1 is equal to a2x squared plus b2x plus c2. But when are two polynomials equal? It's if they're like, x squared terms match, their x terms match, and their constant terms match, right? And so this implies that a1 equals a2, b1 equals b2, and c1 equals c2. So our vectors were equal to begin with, right? Thus, it is 1 to 1. Okay, what about onto? Well, if we have, right here, we would start with something in the target space. So start with some ax squared plus bx plus c. That's an arbitrary element of P2. Well, this is clearly just f of ABC, right? And so we have something that goes to it. So this is equal to f of ABC. And so, yep, it's also onto. So it's a bijection. So that part's good. So then what does this preservation of structure look like? So you would just let, again, two things be in there. So we'll do the same a1, b1, c1, a2, b2, c2. Then it looks like this. Right, so we start by taking f of the sum. Well, this is what it means to do the sum. And then actually apply f. We can then split it up just using distribution and reordering, because addition order doesn't matter. And we see that it equals the sum of the images, okay? And so this shows that it preserves like the property of being additive. And then to do the same thing for scalars. And again, you apply it first inside, take f of it, factor out the r, and then see that this is r times applying f, okay? And so both of those are preserved, and thus this is an isomorphism. So we're going to do one more example really fast here. So an isomorphism from a space to itself is called an automorphism. So I wanted to look at the map from the 2x2 matrices to themselves, given by f of a is its transpose. And here really the 2 doesn't matter. It could be n by n. So 1, is it bijective? So, well, if f of a equals f of b, this means that a transpose equals b transpose. And then you could just do the transpose of both sides, right? This would mean that a equals b. So, yep, it's 1 to 1. And is it onto? Well, if you start with some 2 by 2 matrix, then A is f of A transpose, because A transpose transpose is back to the original. Okay? And then showing that the properties hold, well, f of A plus B is A plus B transpose, but you prove that that was A transpose plus B transpose. And so this is f of A plus f of B. And similarly, scalar multiplication works nicely with transposes, and so if you have f of RA, this is RA transpose, but you just multiplied all of the entries in A by R, and so just factoring that out doesn't change anything. This is R times A transpose, and so this is R times f of A. So this is an example of an automorphism. So for your first exercise, I want you to figure out what Rm, so I guess for what value of m, is it isomorphic to the set of 2 by 2 matrices or space of 2 by 2 matrices? And then give me that explicit function that's going to work and prove that it's an isomorphism. Okay, so let's finish off by looking at a non-example. So here we see an x squared. We square the first coordinate with our function, but keep the second coordinate the same. So why is this not an isomorphism? So it fails to be one-to-one and onto because of the squaring, right? So in this case, we would see that f of negative 1, 0 is equal to f of 1, 0, because both of those give you 1, 0. Also, so this is not one-to-one. It's not onto, since negative 1, 0 is not in the image. It's not f of anything in R2. It also is going to fail linearity, right? Because f of 1, 0 plus 1, 0 is f of 2, 0, which is equal to 4, 0. But f of 1, 0 plus f of 1, 0 is just going to be 1, 0 plus 1, 0 again. It's going to be 2, 0. Right, so this is not equal. This also would show you that scalar multiplication is not going to work. You could do something very similar. So for your last exercise, I want you to show that this function here is not an isomorphism or not an automorphism, since it's again the same space. This one is a bijection though, so I want you to show that it doesn't satisfy one of the other properties. Thank you for watching.